So in the other videos, we talked about transmitting energy, thermal energy, by conduction, convection, and radiation. We're going to look at some quiet cat. We're going to look at some examples. We're going to do some calculations. And just to remind you from the last video, there were these formulas. You may want to write them down again, where P is the rate of energy transfer in watts. That's power. Q is the the actual amount of energy transferred in joules. Delta T is the change in time, usually in seconds. We always do in seconds. K is the thermal conductivity of the material. A is the area of thermal conductivity, so the area of whatever material you're transferring heat through. L is the thickness of the material. Delta T, again, is different. Oh, capital Delta T is difference in temperature. Regular delta, small delta T, that's difference in time. Oh, that's interesting. Q equals MCAT, that stuff, this part. We already said Q is the energy transfer in joules. M is the mass of the material in kilograms. C is the specific heat capacity of the material. We already talked about that. It's a characteristic of the material. And capital delta T is the change in temperature. My roommate's cat is going crazy. So let's start with an example. So here, calculating energy transfer is the first example. Calculate the energy transferred when a block of aluminum at 80 degrees Celsius is placed in 1 liter, 1 kilogram, of water. Oh, 1 liter is 1 kilogram. There you go. There's a transfer conversion. At 25 degrees Celsius if the final temperature becomes 30 degrees Celsius. So there's actually so much information here that I have to piece it out together. So the first thing to do is to list all the known values. That's step one. So I'm going to look at this, list all known values, and I'm going to see and try to pick out what is what. Calculate the energy transferred. So I don't know the energy. I don't know Q. So I'm just going to use those equations. When a block of aluminum at 80 degrees Celsius, so the beginning temperature, that is involved with this. So I'm going to say maybe delta T of the material is 80 degrees Celsius. Sorry, not delta T, but the initial temperature, T sub 0. So T sub 0, the initial, T naught is the initial temperature of the aluminum. I don't know if I'm going to need that. Is placed in a 1 liter kilograms of water. What is that? I'm just going to write it down. We'll see if we need it later. The mass of the water is 1 kilogram. 1 kilogram. So I'm just going to write down mass of water. And I'll see what it is in my equations later. Mass of water is 1 kilogram. What else do I know? And the starting temperature of the water is 25 degrees Celsius, and the final temperature becomes 30 degrees Celsius. Something I do have to mention that's not quite obvious about this is that the initial temperature of the water is 25. The initial temperature of the aluminum is 80. But the final temperature of both becomes 30 degrees Celsius. That's just saying that they're in thermal equilibrium. So we have both of them are 30 degrees Celsius. Okay, so let's write down that stuff. So I have this. I think the cat just ran into the wall. The final temperature for both is 30 degrees Celsius. We do need to know the specific heat. Calculate the energy transferred. If we're talking about energy transferred, remember that was Q. That was Q. So we don't have any power. They didn't tell us anything about power or time. So we're not going to use that. And we're not going to use that. We're not going to use that because we don't have power. We don't have anything with time. So we must use this equation. So that's good to know. So what do I need? I need mass. Oh. I need the specific heat. Oh. Now, something that I found interesting about these, so that's all of the known values. Something that I found interesting, actually, we don't know. We know a little bit more, actually. We know delta T, right? Delta T, maybe I'll write it in green to separate it a little bit. Delta T for the water, that is just, well, what did the water start out? 25. So it's final minus initial. So that'll be 30 degrees Celsius minus 25 degrees Celsius. So delta T of water, delta capital T, is just 5 degrees Celsius. Delta T of the aluminum is 80 degrees Celsius minus 30. No. Yeah. Final minus initial. It actually doesn't matter. We're just going to make it positive. I'll just do 80 because it's the change in temperature. It's not changing in which direction. So we're just going to make it positive. 80 degrees Celsius minus 25 degrees Celsius, and that's 50 degrees. No, sorry, minus 30, right? 25 is the starting temperature for the water, so that equals 50 degrees Celsius. Now I was thinking about this. Wait a minute. Here, there's only one equation. We have two materials. We have water, and we have the aluminum. We know the mass of the water. We don't know the mass of the aluminum. That's crazy. I can look up the specific heat of aluminum. I could look up the specific heat of water. In fact, I only need one of these. I don't have to do two equations. Why is that? That's because the energy transferred between the two is going to be the same, just in opposite directions. So here, Q, you can do it for either substance. You just have to be consistent throughout. If you're going to do delta T, delta capital T, that's a change in temperature for whatever material you're using, and the specific heat is for that same material. So don't mix the two materials with your values here. I mean, you might have to decipher which information you're going to use and which ones you're not going to use. But in this case, we don't know the mass of the aluminum, so we're not going to use the I guess, numbers for aluminum. We're not going to use the qualities of aluminum. We're going to use the qualities of water. All right. Specific heat. I'll have a list, I think, of things. You won't need to look up. You could look up specific heat of certain material. I might have you do that. But the specific heat capacity of water is like the standard one. That's 4,184 joules per kilogram Celsius. Those are the units per kilogram degrees Celsius. And then we can use that equation, I think. Well, let's go on to step 2. Geez, this is a long video. So step 2, I'm going to say it's to state what you want. So you have to reread the question. Calculate the energy transferred. So I want Q. I want the energy transferred. So I'm going to have to use this. And we already decided that, but that's actually step 3. So Q. What do you want? Q, energy transferred. So that's what I want. I want the energy transferred. Step 3 is to choose your equations. Choose your equation. So that one we already decided. We're going to have Q equals MCAT. That's not an A, that's a delta T. And we're going to do it for water, because the energy that's like the Q sub aluminum, the energy that's transferred from the aluminum is the same energy that's transferred to the water. We're assuming this is a perfect system. Nothing's being lost by the container. Like we're pretending that none of the heat is transferred into the container or into the atmosphere here. We're saying it all transfers to the water. So we have that. And then number 4, what's step 4? Is to solve. So you just plug stuff in now. Q for water, that equals, that's an ugly water, the mass of water. Remember, the mass was always in, what was it, kilograms? Yeah, the mass has to be in kilograms. We know that it's 1 kilogram of water. And then the specific heat of water is 4,184 joules per kilogram Celsius, kilogram degrees Celsius, times the temperature difference, right? And the temperature difference for the water was 5 degrees Celsius. So we multiply it by 5 degrees Celsius. So here, look at this. Celsius cancels out. Kilograms cancels out. I'm left with joules. That's perfect because I want the energy transferred. Energy is measured in joules. And so what do you have here? You have like you have 21,000 joules. That's gained by the water. That's gained. If you did this the other way, you might get a negative. If you had that negative, that makes negative. That means the aluminum lost thermal energy. Sweet. But I say quiet, cat. All right. We're gonna move on to the next video. That's quite long. Okay. Goodbye. I said quiet.